Hello everyone, this is Zhongjie. Today I'm going to talk about eTran, an extensible kernel transport with eBPF. This is a joint work from Tsinghua University, Nanjing University, Harvard University, UC Berkeley, and UC Davis. Okay, first, let's take a quick look at the background, how data center transports have evolved. Applications in data centers are constantly evolving and becoming more diverse. For example, microservices heavily rely on RPCs to communicate with each other, typically sending small messages, while storage applications often need to move large volumes of data. As the backbone of data center, transports have to keep up and adapt to different workloads. So, obviously, there's no one-size-fits-all transport. In recent years, we have seen a wave of new transport designs targeting data centers. These transports differ in many aspects, from semantics to congestion control to loss recovery. But here is something interesting we noticed, that for most transports, it takes years to go from a proposal to actually being merged into the kernel. Getting upstreamed into the kernel really matters because that's what gives a transport a real chance of being widely deployed. So the takeaway is, it's hard and slow to extend, customize, or evolve kernel transport. And apart from these examples, most transports never make it. They get stuck as kernel bypass prototype. So why don't we focus on kernel bypass? The most common approach is library OS, where the networking stack runs in the same context as the application. The high performance comes with a lot of problems, such as security concerns, and it often monopolizes system resources. Recently, microkernel-based solutions have gained popularity. It suffers from extra RPC overhead and essentially discarding all existing kernel support. Both of them largely sacrifices the protection and manageability brought by the kernel, which is not friendly to public cloud users. So why is it hard to extend kernel transport? We believe there are three key reasons. The first reason is that the kernel development and maintenance are hard, is low-level, complex, and error-prone. Second, kernel transports often come with kernel overheads, which makes it hard to show the benefits of new transport designs. You may have to spend a lot of time tuning the kernel implementation for transports. Third, if you finish all the above work, getting your code merged is a long journey. The kernel community has a strict review process, and decisions take time. However, kernel transports do offer some very nice properties, such as safety, multi-tenancy, and out-of-the-box deployment. So this work tries to answer how to achieve agile customization, kernel safety, strong protection, and high performance for kernel transport. Fortunately, there is a promising shift happening. Safe kernel extensibility is becoming realistic thanks to eBPF. With eBPF, users can inject statically verified programs into some kernel hooks to modify how the kernel handles events. It's safe, flexible, and already widely adopted. With a strong community, eBPF has a growing impact across many OS subsystems. XDP and AFXDP are two key techniques built on eBPF. XDP handles ultra-fast packet processing directly in the kernel, and AFXDP, on the other hand, allows high-performance packet processing in user space. However, using eBPF to implement kernel transport still comes with several challenges. First, transports, for example, TCP, are very complex. And while eBPF has become more powerful, with new features like dynamic memory allocation, key functions, advanced data structures, it's still challenging to fit everything into eBPF. Second, eBPF and XDP expose only limited operating points for us to work with. For example, XDP lacks queuing and buffering. It also doesn't allow users to craft and send packets proactively in XDP. On top of that, XDP operates only on ingress traffic, and that means any egress traffic simply bypasses the kernel entirely. To address the first challenge, eTran's solution is splitting the transport path. The key insight is that most network transports share a common set of abstractions and components, so eTran separates them into two parts. The first part includes header processing, read and window enforcement, and segmentation or assembly. These components are performance critical, handle the common case, and sit directly in the data path. The second part includes flow management, for example, TCP's handshake, as well as congestion control, loss detection, and recovery. These are not performance critical, deal with real events, and are located in the control path. Following this basic idea, we decided to place the control path in a root privileged user space daemon. This is because it's hard to offload them into the kernel, and they are not performance critical. We then further split the data paths based on their functionalities. Tasks like header processing and read window enforcement, those go into eBPF. Meanwhile, segmentation and assembly, which are too complex for eBPF, are handled in a user space library. Finally, our threat model assumes that applications may be malicious, so we don't trust them. But we do trust the eBPF runtime in the kernel, as well as the root privileged control daemon. The second design of eTran extends the eBPF subsystem, but follows the design philosophy of eBPF to ensure safety and protection. We introduce new XDP hooks. First, there is XDP egress, which intercepts egress traffic before it reaches the network driver. Then, there is XDP gem, which allows sending packets proactively in XDP with efficiency. To support buffering, we also introduce a new BPF map type called packet queue, which provides queuing capability for XDP frames, something previously unavailable. In addition, eTran applies a range of performance optimizations, which you can find detailed in the paper. Okay, this is the overall architecture of eTran. Transports are implemented using XDP along with two new hooks. XDP handles ingress transport logic and receiver-side load balancing. XDP gem handles ACK and credit packets. And XDP egress handles egress transport logic and does rate limiting and pacing. All transport states are maintained in BPF maps. Applications interact with the transport layer through AFXDP, which provides efficient packet I/O. Meanwhile, the control path daemon takes care of eBPF program operations like attaching and detaching transport-specific control events, managing AFXDP resources, and handling a few complex tasks that are impractical to implement inside eBPF. And importantly, untrusted applications have no direct access to transport states, which ensure isolation and protects the system's integrity. Next, let's dive into some details about them. On the left, we can see a code snippet that uses XDP egress and XDP gem. Actually, if you are familiar with XDP, you will find that writing code with these new hooks are very similar to writing traditional XDP programs. They follow all the same eBPF programming constraints, and these hooks reuse most of the existing XDP infrastructures, which makes it easy and familiar for users to adopt. Now, let's take a closer look at the BPF map. This code snippet shows how the map is declared. And this figure shows the memory layout of this map, which is essentially an array whose elements are a linked list of packets. This map only stores frame pointers, not the packet payload. And the user must specify the memory size when the map is created. We use key functions, a set of kernel functions exposed to BPF for all interactions with the BPF map. To implement flow scheduling, the map works in combination with the BPF timer. Based on this abstraction, developers can implement more advanced scheduling strategies, such as portfolio queues, timing wheels, and more. Okay, next, let's briefly go over some extra features of eTran. First, eTran supports multi-tenancy through queue-level resource allocation. This allocation aims to isolate NAPI I/O buffers and avoids monopolizing the NIC. Second, thanks to the magic of XDP, eTran can coexist with other kernel transports. The second feature is traffic management. eTran allows users to leverage the BPF tail core feature to chain multiple subprograms for different tasks, and each subprogram is verified independently by the verifier. Users can submit a policy to the control path daemon, which then updates two BPF map tables and installs the corresponding subprograms into a program array. In this example, a packet first flows through the TCP transport and then passes through a byte counting program and finally reaches a rate limiting program. Okay, and there are more details that are not covered in this talk. See the paper for more information. Thanks. Okay, to demonstrate the extensibility of eTran, we take two representative transports as examples, each reflecting a different transport type. The first is DCTCP, which is connection-based, follows a stream semantic, uses sender-driven congestion control, and exposes a POSIX API. The second is Homa. It's connectionless, follows a message semantic, uses receiver-driven congestion control, and provides an RPC-style API. We implemented eTran with 24 K lines of code, including 2.6 K lines for extending eBPF subsystem. Okay, let's go to the evaluation, which shows the Linux implementation of Homa, Linux TCP, and TAS, a high-performance kernel bypass TCP IP stack. We used bare metal machines on CloudLab running our own customized Linux kernel with two representative workloads. One is RPC workload from the Homa paper and a key-value store application modeled memcached. And this code is open source, free to try it on. We compare the standard Linux implementation of Homa with our eTran-based version. The RPC workload used for testing is dominated by short messages, which is a common case for RPC. We can see that eTran achieves a 3.6 times lower P50 latency than the Linux version, and a 7.5 times lower P99 latency. For workloads consist of large messages, eTran can also outperform the Linux version. For TCP, we compare eTran with both Linux TCP and TAS, the high-performance kernel bypass networking stack. We use the key-value store application from the TAS paper. The results show that eTran achieves significantly lower P50 latency than Linux TCP and also much lower P99 latency. And it can also achieve higher throughput than Linux TCP. Here are the numbers. eTran is only slightly worse than TAS, despite running inside the kernel, thanks to the efficient packet I/O provided with AFXDP and the streamlined, efficient TCP implementation. Finally, let's give a summary of eTran. eTran is an extensible kernel transport system, achieving agile customization, strong protection, kernel safety, and high performance. eTran achieves these goals by extending the eBPF subsystem, hiding transport states inside the kernel, and absorbing techniques from user space transports. Thank you. Okay.